Welcome back. This is the third chapter of lecture 11 and I will talk about the classification matrix. So in the classification matrix you have the actual state of the person and the outcome of the test. So if there is a person who is either healthy or ill, you can test him or her positive or negative or positive. So usually the illness is the positive and the healthy case is the negative test. And then we can define different numbers. So the true negatives are when you are actually healthy and you are tested healthy. So this will be the true negative. On the other hand, when you are actually ill and you are testing positive, then this will be the true positive rate. So these are the two true positive numbers. And then when you're actually healthy, but you are predicted ill, that will be the false positive. And when you are actually ill, but you are tested healthy, that will be the false negative. Maybe this is the most dangerous case. And then here you can see this true negative fraction, which is the number of true negatives over true negative plus false positive. You have the true positive fraction, which is true positive over false negative and true positive. And this will also be the sensitivity, and this is the specificity of the test. So the specificity is from the actually healthy people, how many are actually tested healthy, and for the sensitivity is that from the actually ill people, how many tested ill, tested positive. This will be the sensitivity of our test. So here is an example how to calculate these numbers. You see that in the first model, so our first test is giving from this number of people, the actually healthy people, these 240 people, 230 is tested healthy. So the specificity of this test will be 230 over 240, which is 0.96, which is a very good specificity. For the sensitivity, you have from these 25 actually ill people, only 5 tested positive, which is a very low number. So you see that the specificity was good, but the sensitivity is really poor. So this model, this test, is rather saying that everybody is healthy than actually filtering out the ill people. While the second model, here the specificity is 180 over this 240, which gives us 0.75 specificity, so it is a lower number than before. But for the sensitivity, from 25%, now 20 is tested positive, so it's a lot bigger number. We would say that this might be a better test. We can also calculate the accuracy of a test, which will be true negative plus true positive over all cases. So how many times did we test correctly? This will be the accuracy of the test. If we check the previous examples, we will see that this is 230 plus 5 over the all 265 cases, which is 0.89%. And here the accuracy is 180 plus 20 over this 265, which is 0.75. So in this case, if I'm looking only at the accuracy of the test, I would say that the first one is better. But we have seen that no, we don't like the first test, because here in many cases, many ill people are misdiagnosed, which we don't like. So actually, in this case, the one with the lower accuracy is seeming better. So what can we do with this? We can define a so-called cost matrix. In the cost matrix, we define a cost on misclassifications or even on the right classifications. What can be this cost? If somebody is healthy and these healthy people is actually predicted healthy. This is usually the cheapest thing in this cost matrix. Then even the screening had a price. So this could be said that this is the cost of being healthy and being tested healthy. Then what if somebody is actually ill and is tested ill? In this case, you have to think about the cost of this screening and the cost of the therapy. But this is usually necessary, so we will not price this this case very high. Then we can see the false negative cases, so when somebody is actually ill but tested positive. So in this case, the treatment will be delayed, which gives a lot of cost to our treatments to this diagnosis. Because usually if you are diagnosing something in an early stage, then you have better chances of curing that disease than in later phases of that disease. And on the other hand, when somebody is actually healthy but is tested positive, then you have to again consider that they either start the therapy, which could ruin the health of the person. Just think about the cancer, and you start chemotherapy and radiation therapy, and it will just destroy the person's health. So it could give you a cost. Or if you are sending that person to further screenings, then that will again be in vain, because the person is actually healthy, and it will again add to your overall costs. So the overall cost of your test can be calculated as these costs defined here, which will be numbers you give to your matrix, multiplied by the true negative fraction, false positive fractions, so which we have seen in the first slide of this chapter. So here is an example how to calculate this. Here are the costs. So you see here that if somebody is healthy but is tested healthy, then you define zero cost because, okay, we have done it, now it's okay. If somebody is ill and is tested ill, then you have to go on with the therapy, but it is actually necessary. So you can give a negative cost to it because it's for the better, it's for the greater good. And then if somebody is actually ill but is predicted to be healthy, then your therapy will be delayed and it will have a lot higher cost, which is the worst case scenario in this case. And if somebody is actually healthy, but you are predicting the person to be ill, then again you will have a quite high cost, it's 10, because you have to send the person to further examinations, or you are starting the therapy, which can cause a health risk to the person. And here is how to calculate. So you have these different fractions, true positive fractions, 230 over 240 times 0 plus comes the second one. 10 over 10 plus 230, 10 over this 240 times 10. Then the next term is 20 over 20 plus 5, 25 times 100. And finally, this 5 over 25 times minus 1. And you add all these up together, you have 80.22. In the other case, if you do the same calculations, you will get to 21.7. So you can see that this first test, this first model, is very costly, while the other one is more cost efficient, so it's better for everyone. You would choose this one. Even if its accuracy is worse, we have seen that its sensitivity is a lot better, so you would go for this model, this test, because it costs you less than the first one. And here is what I have told you, that the accuracy of the first one is higher, but its cost is also a lot higher, while the second one has a bit lower accuracy but a lot better cost. So this is the reason you should go with this second model in this case. Now, once we know that we can calculate this cost, we know that this might not be the best threshold we have started with, because what if people here misclassified who are actually ill but are predicted as healthy are getting a delayed treatment that can cost us a lot. So it might be worth it to push this threshold a bit down, and it can save us money. It can be a more cost-efficient way or patient-friendly way to handle things. And how to calculate this? So you do know, you can calculate the expected cost of a classifier. This is what actually we have seen before, how to calculate the cost for the true positive and the true negative cases. So before we have seen the overall cost, but this will be separately for the true positive and the true negative cases. And then you can define that you would like to have the cost of classifying positively lower than the cost of testing negative. And solving these equations, you can come to a simple conclusion, and you can set this threshold value easily using these cost values. So only knowing your cost matrix, you might be able to get this threshold where to say that somebody is healthy or ill. This was the third chapter of lecture 11, and to get to the next chapter, please take the quiz below. Thank you.